planned agenda here is, again, not a heavy load today, practicing matrices, and have your worksheet there. We're going to go through that worksheet. And also mention there's extra credit available for you that want to do a little extra work to bump up that score. I've got 3 problems there, and I can put more there that go back further. That give you credit for just basically preparing for the final. Give you credit for that, and you'll do better on the final as well. And I understand some of the other algebra courses maybe have a little packet of problems to work on. I'll see if I can get that and give you that for practice as well. So you can beef up your score and just know the material better. So you'll do better on the final as well. So you get credit for practicing for the final. How much better could it be? They give you points for preparing for the final. You'll do better on the final, guaranteed, and you can just get points for trying, for working through it, for working through your practice problem. So let's refresh what we did last week, and then we'll move it on. Your worksheet has a few things. And also, for that IXL thing, in case you want to use the mobile app to use that, oh, got a problem. They're printing on both sides. I guess I can't use this. You did check your email for an IXL.com. I signed this up for a trial version, 30-day trial, so it'll last from now till the end. That lets you do practice problems. I discovered this site with practice problems, and I thought, hey, this would be great, give you credit for working on it, and walk you through practice problems. Then I realized, unless you have an account, you can only do like 6 problems, and then it says, oh, sign up if you want to do more. So I signed up, and I signed you up. It's free, so you don't have to pay anything. And that you got an email with your password sent to you. So you can go to that, and I'll show you that link to that. It's over, where is that? Down here. If you click on the first extra credit work adding matrices, just click on that. I think I have a link to the IXL site. You go there, and if you're not signed in, you can sign in with the membership that I have provided for you. So I can keep exploring. You don't have to do a sign up. You can just do a sign in using the password sent to you in your email, and you can then work through little practice problems, such as this. And so I'm asking you, if you want extra credit, just go to that site, work through some practice problems. Can we get this one figured out? Let's see here. 4 times negative 4 is 16. Is negative 16 plus 1. Yeah, that gives us negative 15. 4 times 2 gives us 8. Plus 4 more gives us 12. And see how we did that addition? Didn't have to be a square matrix. The item that goes here is that times that, because this is 4 times negative 4 gives me 16 and an 8. And then adding 16 and 8 to 1 and 4 gives me, or negative 16 and an 8 to 1 and 4 gives me negative 15, and 8 plus 4 gives me 12. See if I got it right. I click submit. My question answered goes up by 1, so I get a smart score. I'm not going to be paying attention to the smart score. All I care is that you work through 20 questions. And when you take a screenshot to prove your work, you basically do this. You can hit the little Windows key and look for a snipping tool. Make a new snip of what you just did. And if you want to get the whole page or just the score, that's fine. Say I just get the score. And then with the snipping tool, before you upload this image of your score, all you got to do is turn on the little pen and just initial it. I'll put my initials there. That's your signature. Yes, this is your work. That's all I'm asking you to do. Actually, you can even show, I suppose once you're logged in, you can show your login as well to show that that was your login. But just do an initial, just saying, hey, I did this work. And that's all you got to do for some extra points for working through some practice problems. How about this one? Think you can solve that one? Let's, you know what I'll do? I'll do a snipping tool of this, and then I can write on it. And now I have my pen. What would the answer be to this one? Well, let's see here. This is a matrix. I don't have to do anything to that. I do have to multiply this one out. So this becomes a 7 and a 14. Oh, but I'm subtracting 7 and a 14 from 6 and 5. So I have to do here, this becomes, I guess you can put the result here. We'll put the result here. The result here becomes, in this position, 6 minus 7. And this position becomes 5 minus 14. And then solving that, that becomes a -1 and a -9. Does that look right? Well, let's find out. Let's go back there and put -1 and a -9 in our practice problem. -1, -9, and double check. Yes, 6 minus 7, 5 minus 14. Sure looks right. And yes, we got the right answer. And we have 2 problems solved. Uh-oh, they gave us a 2 by 2. Let's work through this one here. Capture that in my snipping tool with a new snip. Give yourself some room to work on. And let's see, what would that be? Well, let's multiply this part out first. Then we'll get the rest of it. So multiplying this part out, 5 times all of this gives me, and I'll remember the subtraction later on, 5 times 2 gives me 10. 5 times 4 gives me 20. 5 times 6 gives me 30. 5 times 9, 45. 5 times 5, 25. And 5 times 6, 30. Now I'm subtracting that from this. They've already given me some answers already filled in. I could check that I'm understanding that. Let's just do the fill-in ones. The one up there would be this one minus this one, so that would be a -5. Here would be a 6 in that position minus the 30 minus 24. And the 0 minus the 30 will be minus 30. Does that make sense how I did that? Usually, adding is usually the easier one because all you're doing is doing the numbers in different positions. You're doing chunks, basically chunks of equations because they're giving you the numbers in blocks. The multiplying part, that's the little more complicated one. And that's a whole separate practice that I give you. There's one practice just to go through, just add matrices up. So that'll be easy extra credit points. The multiplication one, we'll do a couple practice. How about we take a look at those ones on your worksheet. And there I have them right over here. I gotta get them from over here. I downloaded them. Where did I put that? Matrix practice 2. There it is. There's your worksheet. Now we're going to do some multiplying. And in this case, I put letters there instead of numbers, just so we do the math without knowing what the numbers are. We just show what the math would be. And this really helps to practice what the multiplying of matrices is. Remember, for every row in the first matrix, we multiply by corresponding items in the column of the second one. So row here gets multiplied by the column here, and then by the column here. This row gets multiplied by each column. So the answer here is going to be this first row multiplied by the first column. So I'll just write in here for my notes, R1 times C1. Well, remember that royal crown, RC Cola. So that becomes AG plus B times I plus C times K. And I can't simplify it anymore because I don't know what those numbers are. I just know that whatever numbers there will be there, that's the number that would go here. Now the next item in that same row is that first same row multiplied by the second column in B. So we'll call this row 1 in A times column 2 in the second matrix. This row times this column, I'll call this C2. This is row 1 multiplies by column 2 one by one. So that then becomes A times H plus B times J. See the going over 1, going down 1, plus C times M. To make it very clear how we multiply arrays. It's a lot of multiplying and adding, and nice thing about this all is once we know how it works, we let our computers do the work when we start doing harder problems. This is just about, in algebra, making sure you understand how it works, and they kind of leave you there and say, okay, then in my calculus and things, we'll use this all over the place. But they want to introduce you to matrices in algebra. So that's the first two elements of that result. Now, if those were numbers, I would be doing all the math. Now, the second row, we'll call that R2, now goes here. R2 times column 1 is what goes in this cell. So row 2, D times the first element of column 1. So that becomes DG plus the second element of row 2 times the second element of column 1 becomes DI. Oh, DG plus, sorry, EI. Third element, F times K. And see how in the first column you always see, oh, it's GIK. GIK is what goes in that second element of the first, because those are the elements in my first column. It's ABC, the first element, DEF, because I'm in the second row. And now this one, again, it's going to be, let's just look at it. It's going to be DEF, that's my first row, times HJM. HJM. And we put a plus in between. Another way to look at that. Elements of my first row, second row, DEF, times the elements of my second column, HJM. Many ways to look at that. And in the final, when they talk about matrices, they also want you to specify, anytime they give you a matrix, they'll often be asking, well, what are the dimensions? Fill in the blanks. Remember, dimensions are always row by column. So we've got 2 rows, and we've got 3 columns. 1, 2, 3. Dimensions here, 3 rows by 2 columns. Whenever I'm multiplying matrices, I have to have the same number of columns here as I do rows here, or I'm not going to be able to multiply them. Those two numbers have to be equal, or I can't multiply them. The columns in the first one has to be the same number of rows in the second one. And the resulting dimension is a 2 by 2. 2 rows by 2 columns. And there's that same rule. I'll have the same number of columns as rows or columns in that one. Now this time it's the same problem, but this time we're given numbers. So let's do the math, and then we'll do the equal sign here, doing the math. Let's do it. Let's show the work just right over here. I'm going to multiply these out. 1 times 1 is 1, plus 2 times a negative 1. And I guess I'll write it with the parentheses times negative 1. See, I'll get the 2 times negative 1, plus 3 times 2. And I might as well do the math. 1 minus 2 gives me a negative 1, plus 6 gives me a 5. 1 minus 2 plus 6. Next one over. Well, 1 times 0 plus 2 times negative 2 plus 3 times 1. 0 minus 4 plus 3 equals a negative 1. And once you start doing a little practice, it's like, okay, I got to get the system down. I'm going to do a slightly different way. Maybe this might be an easier way to think of it. Just write down your elements of row 2 first. Just say, I know it's a 2 times something plus a 3 times something plus a 4 times something. The other something is that first column. The 1, the negative 1, and the 2. If that helps you to see, oh yeah, it's the first elements, it's the elements of my first matrices row, times 1 by 1 the elements of that first column. 1, negative 1, 2. And then put pluses in between them. If that'll help you figure the system out, remember, thinking about it different ways helps your brain to see, oh yeah, that's what it's about. So then I'll do the multiply 2. That becomes a minus 3 and becomes a plus 8. And 2 minus 3 is negative 1. Plus 8 gives me 7. 7 there. And the very last one, I'm going to do that technique again. The 2, 3, and 4 multiplied by the 0, negative 2, 1. And put pluses in between. And then see how that becomes a 0, minus 6 plus 4. Gives me a total minus 2. So, negative 1, negative 2, 5, and a 7. It's a little crowded here. I should have written a little smaller, but that becomes my result. Oh, and then let's go back and fill our dimensions. Row by column, 2 rows by 3 columns, 3 rows by 2 columns. The result, 2 rows by 2 columns. Now, just for a little practice, at just a different order. See, it's the same 2 matrices as we started with, but now we're just changing the order. What are we going to get as a result of that one? Well, just plug through the rules, and let's see what we get. Any questions on any of those first ones, though? So if you feel like it's coming as you start just practicing through. Let's look at that third one then. We've got, well, let's look at our dimensions. We've got 3 rows by 2 columns. 1, 2, 3 rows, 2 columns. This one here has 2 rows by 3 columns. Let's see what our result is. Well, let's just look at the first one. Our first row, the element in the upper corner, is going to be that row multiplied by that column. Well, that's going to look like GA plus HD. And I don't know anything else, so that's all I can simplify to. I do like putting commas in between them as I write it this way. Sometimes you could draw out the grid if you like to make it clear what the solution is in each position. Now, it's going to be GH by those two, and then GH. I'm going to write it this way. GH there, and there's going to be a GH there. And it's going to be added to, this time, a B and E, and a plus in between. There's that column. And a CF with a plus in between. So I'm going to get 3. So I'm going to have 3 columns all the way through. So I know I'm going to get 3 columns in my result. Let's do the next row. Let's do that same technique. I and J is going to be multiplied by each of these columns. So let's just do I, J, I, J, I, J. It's going to be multiplied by A and D, B and E, and C and F, with pluses in between. And let's do that same thing then for that third row, the K and M. All right, so K and M are going to be multiplied and added by some other things. I'll go ahead and put my K and M's in there. You know what? Just so I don't forget, I'll put the plus in there as well. Now, the things they're multiplying by are A and D, B and E, and C and F. So as you go through that, you can think to yourself, okay, I'm going to do GAHD, GVHE, or you can say, okay, I know GH is going to be multiplied and added by things in different rows. However you write it out to come out with, okay, that is the detailed solution. When I don't know what those numbers are, I just write out their letters representing what the numbers will be and then do those little multiplies. And I'll put the square brackets just to remind me that this is all going to be a big array. And now I know my resulting rows is 3 rows. And that's about as big as we get when we're doing problems, is just 3 by 3s. But the problems can get huge, and the smart mathematicians have figured out a whole bunch of things with matrices that have made solutions to very hard problems, huge number of variables, by just cranking through multiplying matrices. So this is just giving you a taste of matrix algebra that is used to solve very hard problems. Just like you have a taste of polynomials and see what they use then in science to solve linear equations, solutions of multiple linear equations. Well, matrices is just another tool to solve those sets of equations. So that was just a practice to get you down with how do you do the multiplying. And now let's just throw some real numbers in there again, just for some practice. And let's do, I like that show what's in each row. So this is going to be, in this one, it's going to be 1 times something plus 2 times something. This is going to be 1 times something plus 2 times something. This is going to be 1 times something plus 2 times something. Now the something is going to be each column here, the -1, the 2 times a -2, the 1 times a 2, and the 2 times a -1, the 1 times a 2, and the 2 times a 2. And maybe before I go to the next row, let's put what the answer is. -1 plus -4 gives me a -5. A 2 minus a 2 gives me a 0. A 2 plus 4 gives me a 6. Now, let's do this row times each one of these things. So I'll throw in my 3 times something plus 2 times something. This is going to be another 3 times something plus 2 times something. And another 3 times something plus 2 times something. Now the something is -1, -2. I always put parentheses around my negative numbers. 3 times 2, 2 times -1, and a 3 times 2, and a 2 times 2. And now multiplying them out and adding, just going through the steps. -3 plus a -4 gives me a -7. 3 times 2 is 6, minus 2 gives me a 4. And a 6 plus a 4 gives me 10. 10, 4, -7, -5, 0, and 6. And all I got to do is my third row, just cranking through the numbers. Again, I'll do it's going to be a 1 times something plus a 0 times something, a 1 times something plus a 0 times something, don't even need to really write out the 0 times something, but just for completeness. And so that biz becomes a -1, a 0 times a -2, 1 times a 2, plus a 0 times a -1, and another 1 times a 2, plus a 0 times a 2. Well, that's a lot easier. That's a -1, that's a 2, and that's a 2. But carefully work through the steps to get the answer. And they are nice. They're pretty nice to you. They only give you like three or four problems like this, and they are not all 3 by 3. But there's at least one 3 by 3 in there. So having practiced a 3 by 3, now when you go to a 2 by 2 times a 2 by 2, you'll feel a lot easier. And I think on the practice page so far I've seen they didn't get much bigger than like a 2 by 3. But I didn't go through 20 of them. I went through the first half a dozen just to see if that was something that might be helpful to you. Getting our dimensions, 3 rows, 2 columns, 1, 2, 2 rows, 3 columns. And maybe we'll come back to this. Let's go back, rest our brain a little bit. We'll go back and look at a little theory. Then we'll come back and practice some more. Sometimes you kind of need to take a little break. Say, okay, why are we doing this? Or let's take a little break from doing the work and let's see how, let them show us. This was back from last week. The easy part. Now adding matrices together, like, oh yeah, math, if I can do the math, oh yeah, adding them together, no big deal. I can almost do that by hand, right? Oh yeah. 4 plus 5, 9. 1 plus 9, 10. 3 plus 0, 3. 2 plus 7, 9. And notice, they're not throwing in the commas. I just do it out of habit. Make sure I know where my columns are separated. And then the difference, same kind of thing. And so, when I'm adding matrices, how big they get doesn't make my problem much harder. It's just doing more addition. And so far, they're not giving you more than 2 matrices to add together. But you can see, I could do a whole rows of matrices. Just remember the particular rules. They all must have the same number of rows and columns, or you can't add them together. So dimensions must be equal. The same. You can't add them together if they're not exactly the same size. They don't have to be square. They just have to have the same number of rows and columns, or you can't multiply them together. They threw in, then, okay, remember, when I multiply or scale the matrix, I'm simply multiplying everything in my matrix times a particular number. And the example they use is, I'm needing 15% more equipment for next year. And I have my list of my equipment. They try to throw, oh, this is an example problem. All we care about in the math part is we take that matrix and we multiply it by 15% or 0.15. When I multiply by 0.15 or 15%, that tells me what my increase is of all my equipment. Now, what the numbers represent out there in the real world doesn't matter to the mathematician, doesn't matter to the calculator. When we're doing matrix math, we just do the numbers and then go back and say, okay, 15% more of these numbers, oh, that means 50% more computers, tables, and chairs for lab A and column A and lab B and column B. But we did the math by just doing a scalar multiply of my chunk of numbers that out there in the real world represent something. So we go into the abstract math, do the numbers, and then we come back to the real world and say, wait a minute, we can't buy half a desk. We have to at least have 3 computers if that's what the 15% increase needs. So they do the rounding up because back into the real world, we have to have integer numbers of computers, desks, and chairs, or computers, tables, and chairs. But the math part gives me scalar multiply. So this is scaling the numbers in that table. Now, if you get into graphics, computer graphics, and matrices having to do with computer gaming and the drawing of pictures and 3D graphics, scaling there actually becomes the scaling of the dimensions of the graphic that I'm drawing. Or if I'm aiming a rocket, the scaling of dimensions is think of it as adding more fuel to get the rocket to go further. And I need to multiply everything. How fast it goes means I need more power, and it will get me there. I'm scaling my results. So depending on what problem we're solving, scaling can be stretching a line on a drawing or adding more power, and everything in my chemistry happens faster or bigger by scaling everything up. When I'm cooking a recipe, I scale it up. I have my matrix of ingredients. You have your recipe for 2 people. I'm scaling it up. When I'm cooking for 20 people, I multiply by 10. That's all scaling is. I have chunks of numbers that represent something. Could be ingredients, could be the molar number of milliliters of all my ingredients for my chemistry experiment. Everything gets scaled up. Now the numbers Hopefully we're measuring them and getting the correct numbers. And we have to see, does it scale linearly? Well, that's all having to do with the figuring out the chemistry. But when I do the math, scaling is just multiplying each member by that scale factor. So I can do what looks like polynomials with matrices. I can add matrices that have been scaled by a certain amount, and the order that I do them doesn't matter. I can multiply the matrices and then scale, or add them together first and then scale. So just to relax our brain and review what we did last time, remember, scalar 3 just means I multiply everything by 3. So that becomes, when I do a multiply by 3, I just get everything in there multiplied by 3. 24, 3, 15, and 12. Scale by 3. That's the scalar. And all to prepare for doing polynomials. Multiply by a negative number, no big deal. I'm just multiplying it by a negative 2. Everything in there gets multiplied by a negative 2, negative 8, negative 2, negative 6, negative 4. Scaling, and then I can then do sum of scaled matrices. I can solve this problem. 3a plus 2b. Just by multiplying everything in here by 3, and then everything here by 2, and then adding them together. And I think we did this on the page last time. And then they go over again, the multiplying. Now I'm hoping now that we've done some practice, when you see something really scary looking like this, it's not so scary to you. I call them A, B, C, D, E, F. They like to give them A1, 1 in row 1, column 1, row 1, column 2, row 1, column 3. But it's just as though I gave it A, B, C, D, E, F. The multiplying out, you're just saying, okay, the location numbers are those rows and columns. Multiply each element, multiplied and added together. So they're just showing you that rule of multiplying matrices in a kind of a scary looking notation. But now that we've done a few practice, I'm hoping, okay, this a lot of writing, a lot of numbers, but it's not so scary anymore because we've done some practice. Notice here, this can be one matrix. I don't have this, they're representing one row by a column. But if I'm multiplying a 1 row by 3 column times a 3 column by, or 1 row by 3 column times a 1 column by 3 row, I get one number. I get a 1 by 1 result. See how this is a 1 row by 3 column? And this is a 3 row by 1 column. My result is just that one element. And when I just pack them together in a big chunk, I get a 2 by 2 when I'm multiplying a 2 by 3 times a 3 by 3. So back in my multiplying out matrices now, notice, remember the capital letters represents a chunk of numbers now. But just like we can do with regular algebra, my chunks of numbers still follow the rules of associating the grouping of the different ones. I can do AB first and then C, or do A and then BC. But, and it's distributed, but I can't switch them around. It is not commutative. They only mention the order that I do them, or the grouping of how I do them, doesn't matter. How I distribute the grouping, add them and then multiply, or add and multiply. But notice, CA and CB. CA is not always going to be. CA may not be AC. The order may not be true. Sometimes this may happen, but we can't guarantee, because sometimes you'll get a different answer when I change the order. So this is the part that's different from regular algebra with matrices. The association, the grouping of them, doesn't matter. The distributive property doesn't matter, but the order will matter. So this is something that they're saying right there. Not commutative. And that means AC is not guaranteed to be equal to CA. Some matrices it will be. Just like some numbers have special properties. So we've already done some practice multiplying. Let's just do a practice multiply by 2 again, 2 by 2 by 2 by 2. And then we'll get into the representation of augmented matrices. So again, let's just do that real quick. 1 times 5 plus 2 times 7. And 1 times 6 plus 2 times 8. A 3 times 5 plus 4 times 7. And then a 3 times 6 plus 4 times 8. Calculating those numbers, then I get 5 plus 14, 19, 6 plus 16, 22, 15 plus 28, 43, 18 plus 24, 18 plus 24, that sounds like 42. Don't worry about needing to do the math in your head. Just doing the recognizing what math we do. Getting to this part, that's something you need to be able to do. But then, once you get this far, don't worry that you need to do more work. Show the work of, hey, that's a 5 plus a 14. Don't worry that you want to add more. You don't have to do it all in your head. You can even use your calculator for 18 plus 24. Don't be embarrassed. You stop there. Okay, calculator. You want to do the math? 28. Go ahead and do that. Don't think you have to do it all in your head. Me and my little nerd friends, we would try to do it in our head, and of course, half the time we'd mess up because we thought we were good and we're racing each other. So carefully do that. Use your calculator if you need to. Now this is a strange one. It's only because I think the way the printing came out, there's not a 0 sitting there. Sometimes they'll leave a blank there, but this is actually a 2 by 3 column. Somehow the printing came out bad. So that row times that column, that row times that column. So what do I get as a result? Let's see here. This row times each of those columns. So this is a 2 row by 3. This is a 3 row by 2. Or sorry, this is the 3 by 2. My result is going to be a 2 by 2 in my result. I'm not going to make you go through another multiply because you've been practicing that already. This is demonstrating that AB and BA are not going to be equal. I can multiply AB and BA and they show me my result. But notice, AB gives me a 2 by 2. BA gives me even a different size matrix. So definitely not commutative. Again, another demonstration of you change the order around, you'll get a completely different answer. And that's one of the things that makes matrix math a little bit more complicated. But you don't have to do a ton more with this except understand the rules of matrices. Now let's go back. Well, I guess we got a practical problem here. Then we'll look at the problem I gave on the worksheet on the back side. That these problems are actually representing equations. In this case, we have prices of things that are going to go with goals, balls, jerseys. Wildcats have the requirements for numbers of equipment. We have prices. So in order to calculate prices, notice I don't want to, even though it looks like, oh, that should be a column matrix. No. If I have goals, balls, jerseys here, and I'm going to represent it by this matrix, my costs are in a row, and if I'm going to get costs for one item at a time, I need to put C on the left side. And it has to be a row of numbers, so I get 300 times the price of goals, plus 10 times the price, or times the number of balls I need, plus the $30 times the number of jerseys I need. So they put the numbers in matrices, but then you have to think very, very carefully, knowing what the numbers represent, and what I'm looking for is what's going to be the cost that I need to spend for each team. I need to get a 1x3 matrix result, or actually a 1x2 matrix result. What's the total cost? So CE is what I'm looking for to represent the cost for each team. Remember, the result here in this particular problem is the cost for the Wildcats and the cost for the Mudcats. My result I'm looking for is Mudcats cost, Mudcats, the number of their budget, and the Wildcats budget. So I had to put the costs of each item in a row matrix because of how the problem is $300 for every goal, $10 for every ball, $30 for every jersey. That's the part that you don't have to worry about in this class, is how to set up the word problem. They're not going to give you a word problem with these numbers. Because that's even regular word problems are challenging, right? I remember some people I know, they just hated those word problems. My nerdy friends and I, we kind of liked the word problems because they were a little more challenging. But they're not going to give you, hey, here's a bunch of numbers, figure it out in matrices. They laid out the problem of, okay, here's the two matrices. Now, when you have this problem, now you take it from here and do the multiply. And then they even show you how they do that multiply. Now, they can do all this on a calculator, but let's jump to that second page of that practice. We'll skip this one. We'll come back to this to give us a little bit of warm down. Let's look at what in the world this is and see if we can make it into something we're familiar with. We have this matrix A that I just told you. Here's a matrix A. And here is B. It's X and Y. And here's a matrix C. Well, what do you mean? Solve for XY given AB equals C. Well, let's do, what does AB look like? So let's multiply out AB. Well, AB is 1 times X plus 3 times Y. All right? 1x plus 3y. That's that one row times that column. And there's no other columns, so I go down to the next row now in my result. Negative 1 times x plus 5 times y. And I'm saying that is equal to c. Well, that's the same as saying 1x plus 3, let's see it this way. There's that matrix there, equals c to 6. Well, basically that's the same as saying x plus 3y equals 2 and negative x plus 5y equals 6. Hey, that's looking familiar, right? We've seen polynomial, a system of polynomial equations. Two equations, two unknowns. Well, let's use our polynomial solving skills. Look, if I add these two together, the x's will add to 0, and I get 0x plus 8y equals 8. And I can solve for y, divide both sides by 8, and I get y equals 1. And now I can come back and substitute in any of these equations. I can say x plus 3 equals 2, because 3 times 1, now that I have a y is equal to 1. X plus 3 equals 2, or x equals negative 1. Subtract 3 from both sides. X equals negative 1. So now I know my solution is, and I'll put the solution over here in a point, negative 1, 1. That is my solution to what was a matrix problem. So the point of matrices is it's a way to solve what they call this a system of linear equations. Putting it in matrix form is just another way of looking at the numbers, and then we can crank our rules about matrices that the smart mathematicians have figured out for even huge systems of linear equations. This is just showing you that I can go from a matrix equation back to something I've seen before. And of course, the whole point is I can go from here to a matrix problem. And that's where they're taking us, is I have a system of linear equations. I can turn that into a matrix problem. And they call this thing, those two matrices over there, they call that the augmented matrix. But let's go the direction of something and turn that into something we've seen before to try to help you see that connection. And then when you talk about augmented matrices, I'm hoping that it'll just be like, oh yeah, that augmented matrices, I see why they did that. It basically turns that into a matrix problem. So solving for x and y, once I'm here, it's like, oh yeah, I've been here before. This is the world I've been familiar with. The matrix world is just another way of looking at these problems. Putting it in matrix form is the exact same problem. Let's do the same thing with this one. The reason I love the 3x3 is when I'm doing graphics, this is two-dimensional graphics if it's a graphics problem. Drawing circles and triangles and a lot of cool stuff. But when I'm doing 3D graphics, which is a lot more fun, I'm dealing with 3x3 matrices. And letting the computer do all this work. And all we have to do is be kind of familiar with why the computer is doing it this way. Do you think we can figure out this one? Well, you're not being asked to solve for x, y, and z. All you're being asked to do is write out the three equations that it represents. Don't worry when you see this, oh, I got to solve for x, y, z. When we see this, let's put it in the familiar systems of linear equations. So, 1, 1, 1 times x, y, and z. Oh, that's the same as x plus y plus z equals 6. See how 1, 1, 1 is 1 times x plus 1 times y plus 1 times z. And that one row is equal to 6 in the C array. Now, even though 0 times x gives me nothing, and I often leave this blank, what you'll see, just so we have the pieces of our linear equations lining up, we'll leave a blank there, and we'll do a 0 times x plus 2 times y. We'll put that right here under the y's. We'll get all our y's lined up carefully, leaving a spot reminding you, oh yeah, there's a 0 here. But often you'll see that left blank. And so it's a 0 times x, we leave blank, plus 2 times y, plus 5 times z. And that is equal to that row. And then that last row will be 2 times x plus 5 times y minus 1 times z equals 27. If you want to put brackets around that and call that the C matrix, that's just fine. This, if you want to call this is A times B, that's also just fine. But notice that A times B it better be the same dimension as this array, or I have an invalid equation. Remember, these all add to one number, so yes, I'll get a 3 row by 1 column times a 3 it is equal to a 3 row by 1 column here. Here I'm multiplying a 3 by 3 matrix by a 3 by 1. My result is a 3 by 1 dimension. And I can't set equality unless they turn out to be the same dimension. So I'm comparing a 3 by 1 is equal to a 3 by 1. Yes, it's a valid equality. So now for your job is, given a system of equations like this, can you go this direction? Just like in math, we figure out, okay, is this a hard problem or is this the harder problem? They represent the same problem. System of linear equations can be represented by this. And we call this, when we put these together, these numbers, this matrix times x, y, z is equal to this matrix. We'll put the A and the C together, and they'll show you this kind of format. A and the C together as one big array. That is what we're going to call our augmented matrix. A shorthand way of representing this system of linear equations. I have this big array. It's going to be multiplied by my 3 unknowns. I'm deciding to call them x, y, z for now, but they don't have to be x, y, z. And I set that to be equal to some result. I put those together into a 3 by 4 matrix. Typically, that's my representation of a system of linear equations. So let's look at how the textbook explains this. The textbook is pretty short for this section. So let's see how they represent that. They first start with a simple equation that has no solution, yet because we only have one equation but 2 unknowns. We don't know what x and y are. There's a whole bunch of x and y's that satisfy this because that is a graph of a line. That's a linear equation. So that's some line somewhere on a graph. We don't know what x and y we're looking for. We just know that 3x plus 2y equals 5, or we have the 3 and 2 array times the x and y array equals 5. That is my array. They say, well, throw out the x and y's, put these two together, and we call this our augmented matrix. In the simple one equation representing a line. It doesn't make me very happy because I want to know an exact x and y. When I have two unknowns, I want to have two equations. So I like the square matrix, but this still is a valid augmented matrix representing that equation. So think of the augmented matrix as they're hiding what the two unknowns are. And often when I was doing it, they would draw a little dotted line between these to remind you this is the left side of the equation, this is the right side of the equation. But in this textbook, they're just saying, you see that equation? Turn that into that augmented matrix. When you see this equation, well, you basically just look at the multipliers of each x and y and turn that into a 3, -1, 2, and a 3. And then equals, we hide the part about that x and y in there, and we just throw in the other column is the 7 and the 1. So that becomes our augmented matrix. So I'll erase that part and maybe make that a dotted line. Just to remind you that 7 and a 1 is the part that represents that. So the 7 and a 1 becomes that last column. This is the part representing what's multiplying. What are the factors of the x and the y's? Or call it the unknowns. Because it doesn't matter what x and y, what letters you use to represent what solves this. X and y is just a popular, x, y, and z are the popular ones. But the augmented matrix reminds us that, hey, we've got two unknowns. Call them x, y if you want, a or b. But the augmented matrix represents this system of linear equations. So you will be asked to go from here, some system of linear equations, to the augmented matrix. And in the little practice problem I gave you, I went matrix to system of linear equations, hopefully making that connection a little clearer. And that's as far as they're going to take you in matrices in Algebra 2. They don't make you do a lot more. They just go up to 3 by 3. So let's look at this one, and we'll check our answer here. We've got 3 equations and 3 unknowns. So I'm going to make room for 3 things in my columns, and it's going to be 3 by 3. Even though this only has 2 things in there, I'm going to leave room for the z part because this one had a z part. So I'm going to turn this into 1x, 2 y's, and 0 z's. I do need to put the 0 in my augmented matrix. Even though they leave it blank here, remember that represents 0 of the third unknown in my 3 equations, 3 unknowns. So don't forget, when you don't have a z, you still need to throw that into your augmented part. There's the 6 times x, and they're being nice to us. They haven't reordered them. The -1 times y, and there is 7z in that one, that second equation. And there's no x's in this one, so I put a 0 in the x part, 5 in the y part, and a -4 in the z part. And now that last column is what those 3 equations are set to be equal to, 9, 16, and 12. Basically putting a system of linear equations, that's what this is, system of linear equations. Linear because there are no squareds of x, y, or z, only the first power of all my x, y's, and z's. And there are 3 unknowns, x, y, z, and I have 3 equations. So it is solvable, 3 equations, 3 unknowns. Put it into that augmented format. And so they show us walking through that. Let's see, they basically showed you the 0z. You want to throw in there, just to remind you where there are zeros. keeping the columns in line. The Y's have a Y column, have an X column, have a Z column. Keep those lined up, and then it's easy to come up with your augmented matrix. That's been a lot to go over. Let's do the last few practice problems just as we warm down our brains with all this stuff. The plan for Thursday is to just do review. Everything's review Thursday. And if you have any problems that have been tough for you, I'd love it if you send me an email first, and then I could have all ready to go some practice problems on things that are a little challenging to you. You can even write it down on your notes now as you hand those in for your attendance. Just say, can we work on some of these problems? These are the ones I've had a tough time with. I'll make sure we work on those on Thursday. So yeah, make any notes of, hey, what problems would you like to see? And there are also some packets, as I mentioned at the start, for extra credit. But let's just do these last ones as we warm down. Let's just do the multiplying out. So multiply AB to find the values for C. Well, let's see here. What do we get? 1 times 5. I'm going to do it this way. I'm going to do the 1, 1, 1 times 5, 3, 2. And negative 2. 0, 2, 5. Times 5, 3, negative 2. And a 2, 5, negative 1 times 5, 3, negative 2. And what do I get? And of course, I'm adding all those things together. What do I get? 5 plus 3, 8, minus 2, 6. 0, 6 minus 10 gives me negative 4. 10 plus 15 plus a minus 1 times a minus 2 plus another 2 gives me 27. An interesting array that, if we look to the one just above it, these show that this is the solution to that equation up above. That if I have a 5, 3, and a negative 2 for x, y, z, I get 6, negative 4, 27. There's a lot of work that went between here and knowing 5, 3, and negative 2 that you don't have to worry about. That's something that they deal with, how to solve systems of linear equations using matrices. Find the inverse and the augmented matrix and the determinant. That's all pre-calculus. All you need to know is that's how we got matrices. How matrices help us solve problems. This was taken from that little practice site. Find the missing number. Well, I don't even need to worry about that one. They give me that one. I'm just worried about 8 minus 4 times 7 minus 28. And that would be 8 minus 28 gives me minus 20. This one, there's just 2 to fill in. I just care about that one. Negative 2 plus 20. Oh, that becomes 18. This one becomes 3 plus 4 times 0. 3 plus 4 times 0, or 3. Adding these together, oh, I still got to do the multiply. Why don't we just do the multiply down here below it? That becomes 20, 24, 0, 0. There we go. Negative 2 plus 20, 18. Oh, it's the same problem. 6, 0, 3 plus 0, 3. That wasn't supposed to be the same problem. Made it too easy for you. Think you could do that last one? Yep.
The screenshot of the stuff, where do we turn that in?
Oh, on Moodle. There should be an upload there. Right at the extra. Let me check that. If you go to Moodle, let me check that. There, if you go down to that problem.
There's just 3 different ones, so I didn't know.
Yeah, each one has an upload. Yeah, so each one, you don't have to do them all. You want to work on the one. But yeah, just go to that and then click the upload. And then upload your solution. Work through the problems. Let me go show you how that would work. Say I solved 2 problems. I'm going to use my snipping tool. Actually, if I log in, it'll even show my login. So if you do log in, that's probably best. I'll go ahead and log in here. Because you have your user password. Let's see. Does it give me a login? There's my sign in. I remember my login now. Oh, got it. Bad character in my login, that's why. I think that's my password. There we go. And let's see, if I get a picture of that. Oh, it doesn't show me, my name at the top. Okay, I was hoping it would show my name at the top if I did the problem, and then if you did your screenshot. Suppose you answer this question, that'd be 5, -2, that'd be -10 plus a 0, that'd be -10. Submit, I get the, woohoo, you did great, and I have a score of 1. Let's pretend I did 20 of them. I'll do the snipping tool, snipping tool, new snip, and since my name isn't showing up, just basically do a snip of that. Hey, I've solved 24 problems, there's my score. Make sure it shows your score. And then here with the pen in the snipping tool, you can just put your initials. Draw a smiley face if you like. And save that, Control S, and upload that image. And you'll get credit for just practicing and making yourself better able to ace that final. All right? That's all the new stuff. Just turn that in. I use that for attendance, and I love any comments about what should we practice more on Thursday. Otherwise, I'll pick probably logarithms because those are kind of tough, and maybe go back a little bit to the things that have probably gotten a little fuzzy. If matrices, I still need to practice matrices, I can do a few of those, but I'm thinking today was probably the last practice for matrices, unless you think we need to do more. Yeah.
For those who just have to answer like 20 questions, right?
Yeah, just 20 problems, and then your score will show up. I did 20, and you had, it doesn't even matter what this score is. Meaning that, hey, you did 20. They're fairly easy, but it's about the level of what I'm seeing they're going to have for you on the final. So. All right, have a great day.
Keeping this one?
Yeah. And put your name on it, and basically I count that as attendance, and I'll hand it back to you Thursday. Otherwise, I'll pick problems that I think because I know what's on the final, and I'll make sure we practice.